All right, today we're going to talk about the HK61 PCB blower control board. Now, the blower control board has been an evolution from the relay that had the board on it to the last one we did where it had integrated a few park terminals, M1 and M2, and the transformer is now integrating through the boards. You can now put a fuse block. It has a fuse block holder, so you can put a 5 amp or 3 amp fuse on it, depending on what the manufacturer's suggested fuse size should carry. And Carrier has many products. They have their ICP, their International Comfort Products, which is pretty much your comfort makers, Temp Stars, Carrier, Payne, Bryant, it goes on and on. Long story short, you'll find this board on every single one of those from the timeline of 2000 all the way up to about probably 2010, safe to say. Maybe 2012 is when they may have cut that off. And they did that over the course of using the PSC for a motor and also ECM for a motor. So they eventually just did away with it altogether and just put everything in the backside of that motor. But you get to see this transition here from a PSC to an ECM using the same blower component. That blower component was to turn the blower on and turn the blower off and allow the relay to stay closed for a little bit. We're going to take this to the CANTEX box and we're going to teach you every one of these points and a couple of tips and tricks, and we're going to take it to a blower motor and we're going to wire it up in that perspective, and then we're going to take it to the smart board and we're going to draw this out wire by wire where things are input and output, and go over some tips and tricks there. Stay tuned. Okay, we're at the CANTEX box. Today we're going to go over the HK61E. Basically, it's a power control board, so it's a PCB board. However, you'll find these mostly in comfort makers, Carrier products. This board's been out for a very long time, so it's working on PSC motors. It worked on ECM motors for a while. It's a good board. The board has an integrated fuse on it. So basically it receives 24 volts from the transformer, and then as long as the fuse is closed, it puts 24 volts back out, and it gets a call for G. And basically with that call for G, there's no delay when it gets the call. It immediately brings the fan on, the blower motor on. But when you lose that call for G, just like the other boards, there's a time delay. Now this time delay is 90 seconds. So we're getting a little bit more efficiency out of our evaporator coil, whether it's in heat mode or cool mode. So we're gonna wire this up and we're gonna go over the terminals here that are on the relay of the board. We have our common terminal. We have our NO, which is normally open, okay? So power is only present here when we get the call for G. We have our normally closed terminal, which power is always present between common and normally closed. So if you wanted to use that for something in building automation, like a light or something like that, or another load that needs a leg of power, you have that available to you. However, when you wire it in your Carrier unit, you're not going to wire it to the normally closed. You'll wire common to here and normally open to your fan speed, which will either be medium, high speed, or low speed. Typically high speed or medium speed are the only two speeds you use for heat pumps or air conditioners. There is normally a plug that goes on here. We have these small pins, so we're gonna have to be very careful when we put our alligator clips on there and we start energizing these terminals, and we'll go over their inputs and their outputs. If you look here, they have 3 C's. Those are your commons. So that's a path back to the transformer. So if I have C over here, that's the same as the C over here. So this is low voltage common. There's 3 of them, 1, 2, and then 3. Then we come down to the T terminal. That T terminal is for the transformer. So R from the transformer will power I'm going to just move my meter so you can see that I have R here. R from the transformer will power up the T. And then as long as this fuse is closed, we'll release 24 volts down here on R, which typically would wire over to your float switch, out of your float switch, and then to your thermostat. Once your thermostat gives the call for G, the one that we haven't gone over here, the G terminal, that will be an input which will close between common and normally open. And then once you lose that G, the countdown begins. So with that being said, we're going to wire it up. But before we do that, we're going to go ahead and go over the CANTEX box just a little bit. We have our power supply, L1, L2. Our goal is to bring 240 volts power here up to T1 and T2. Once we do that, we'll have 240 volts and our magical 120 volt light will come on, as long as there's a leg of power on each one of these. We have R and C, which is our 24 volts. 24 volts is coming from a transformer to provide that secondary voltage that we're going to need to allow our board to work. Now, I don't need a thermostat to do any of that. We should understand low voltage to the degree where we know where 24 volts G is coming from. So we can simulate a thermostat by just putting 24 volts on G. Getting right into it, we're going to go ahead and wire our legs of power up to T1 and T2. So we're going to take L2 to T2. We're going to take L1 to T1. Now once I do this, the light's going to come on. I'll just touch it first. There you go. I'm going to go ahead and connect this back down here for a second. And before I go any further, let me go ahead and demonstrate power. Between L1 and L2, we have 238 volts. Okay. Between R and C, we have 27 volts. All right, so now we're not going to just put 240 volts up here and let our light come on, because that light won't shut off. We have to control it somehow. And the only way to control that is to go across a relay. So we're going to take L1 and we're going to go ahead and run it over to common on the board. Okay. And now with that being said, the relay is open. So between normally open and L2, I should read my 240. I'm sorry, normally closed in L2, I should read my 240. With that, we know that we're already making across the normally closed side. So I'm going to go ahead and just finish wiring T1, but I'm going to wire it up to the normally closed terminal just to show you that, you know, power is always present on this terminal right here. And we're just going to go ahead and connect it. And so be careful with just hooking anything up to that. You want to make sure that you understand that that is normally closed, means there is always power there, unless we're getting low voltage calling for the relay to close the normally open portion. And when that happens, the normally closed portion opens up. Okay, it's just a single pole relay, and it can't throw in two different directions. It's thrown in one direction. Right now, it's in the normally closed position. Where we want to wire this to is normally open. So I'm going to go ahead and just connect right here to normally open. Give me a second here. Don't have a whole lot of space to go connecting wires. Just bear with me. looks like that's going to work. Okay, so we're going to go ahead and connect back to T1. Now, I do not have anything closed here, so my load's not going to activate. The next thing we're going to do is we're going to go ahead and hook up the low voltage side. We're going to take our green wire, and I'm going to go ahead and use this for common. So I have 3 commons. I'm just going to carefully just connect a couple of these, and I'm going to run that up. Okay, and now I have T, which is my transformer. That's the very next one that I want to wire to. So I'm going to take, and I'm going to wire from T. And make sure I have a good connection where I can push some of this insulation, because I don't want to touch these other wires yet, or these other pins. Normally you have a plug here, so you're just going to connect to the wires. I don't have that plug for the demonstration of trying to show you the individual terminals. All right, so I'm going to go ahead and show you now that because my fuse is in there and my fuse is closed, I will read 24 volts on R. So down at the very bottom prong, all right, I'm going to go ahead and take one lead and put it on common, and I'm going to touch R, and you'll see I have 27 volts there. So that's my voltage output that I would wire to my float switch, out of my float switch to my thermostat, and then coming back from the thermostat, I'll energize the G terminal. Now, another way to do this too is I can simply just bridge a connection, like I just jumped out between R and G. And if you notice, the load came on, and it is in a off cycle right now. So because I have 24 volts on my board, I'm able to hold the relay in the closed position, even though it's not being told to come on, to energize the normally open terminal closed, energizing my load. I'm able to do that for 1 minute and 30 seconds or 90 seconds. Now, 90 seconds is a very long time if you're not looking at a stopwatch or something like that to pace yourself from jumping the gun. Basically, it's very easy to misdiagnose these within a minute and a half. A minute and a half is a very long time. It's like watching water boil. But we're going to sit through it, and if I wanted to know, hey, is my relay on my board sticking? Is this board failed? The best way to do that would be to put a timer on it. And if you know it starts off with a 90-second off delay, and it's taken 5 minutes, an hour, or whatever, then you obviously need to replace the board. Now, there is a, if you look on the far right-hand side on the corner of the screen, I have the board up there. You'll see JW1, and there is a little, I'm going to go ahead and get the camera in there so you can see it. I don't think you can see it on this side of the fuse. But if you look there, right to the right-hand side of that fuse, you'll see a little piece of metal pole there, like it's just a short that is creating from here. All right, this is what I'm talking about, and that is the JW1. If I were to take some snips and just snip that so it's not shorted out right there, what that would do for me is it'll take that time delay that we just experienced, it'll take it away. And that's basically how that works. So we obviously want our time delay because we're going to get more efficiency out of our coil. And when we take this to the smart board, we'll map that out to see what kind of efficiency we're looking at. We're going to go ahead and do this one more time, and I'm going to just short between R and G, and I'm going to leave my lead there. And what we're going to do is we're going to go ahead and just look and see what that off time is. So if I were to release and hit start at the same time, you should see 1 minute and 30 seconds before the load comes off. So we're going to go ahead and release it. We're going to hit start, and we are in an off delay right now. The last time we didn't have our timer up there. We just wanted to show you what a 1.5 minutes felt like, which is very easy to get to that point and then misdiagnose. So it's very important as a technician to, know your delays, and typically you're not going to go more than 1.5 minutes on. So this is pretty much one of your longest delays you can have on a motor. So remember that tip. Typically you're never going to go beyond 1.5 minutes. 90 seconds is about max. So if you come up to this thing and it's still running and you see there is no power on G, like I have no power on G, right? So I know I'm not getting a call. And so if I can get my phone out and replicate this problem and I'm sticking because it doesn't open after 1.5 minutes, then I need to replace my board. Now, if you have a customer that has this board and they do not like that time delay, you could just take your pair of snips and just break that connection on that J1 terminal, and that'll end that time delay. It'll just be constantly on or off. It won't have a constant off delay. So we should shut off any second now. Yeah, and so this is pretty consistent. 1.5 minutes, very long time. Now the reason why I took my test leads and I kept on jumping between the R and the G is, remember, I don't have a plug here. So I'm not going to wire all these to this, because it's going to confuse you. You won't even be able to read the letters on the right hand side over here between the fuse and the where the plug would be. But two, I don't have a whole lot of space to come over here and come out with R and then come back in here with G. You can kind of see how that would be very tight and very difficult, also very dangerous. So for what we're trying to demonstrate, we're putting power on G, we're releasing power on G, and we're trying to show you that it is normal for these to have a off delay. Now the fuse, if the fuse ever goes bad, immediately your delay is gone. I'm going to go ahead and pull it. You lose your delay immediately. I'm going to go ahead and take the fuse, which is 5 amps. If this is ever bad, you have an electrical short. Make sure that you do not put a larger size fuse just because it fits, like a 15 amp or a 7.5 or 10 amp or anything like that, because if it calls for a 5, it's there to protect the transformer and protect all the low voltage components that are in the circuit. And so we want to make sure that we're not bypassing that. Now, for the purpose of this video, I'm going to go ahead and show you that I can jump here. Not that we recommend you ever do this, but the moment I do that, I'm now closing across those terminals, and now I can sit here and give it a G call, and I'll run. Now the moment I open this, we lose 24 volts, and the board has no power to keep the relay to energize. So it's pretty neat how that works. So the R and the T are in line with the fuse. So T is an input. At this point, I'm going to show you here, because we have power on T. All right, I'm going to go ahead and put one lead on common. I'm going to come over here to the top where my fuse was. You see I have 27 volts there. I don't have anything there. And therefore I'll come down here to R and I have nothing on my output. But the moment we put power back on here across the fuse, which is creating a closed circuit, I'm going to come back up here to common. On one side of the fuse, I have 27 volts. On the other side of the fuse, I have 27 volts. And as a result of that, I have R giving me 27 volts as an output. And so, again, I'm just going to take R and G and just jump them. So I'm taking this 24 volts and I'm supplying G 24 volts. And yeah, so if you're toggling G on this board, every time you do that, you're going to go through a 90-second time delay on off cycle. So if somebody's trying to diagnose this and they're, you know, uh, de-energizing G and energizing G by the wire nuts that are in the top right-hand corner of your cabinet, and if you're a little confused, you know, you can easily misdiagnose this because every time you give G 24 volts, your board is going to close the relay, and even though you break that power, it is going to keep that relay closed for a 90-second countdown. And I don't think a lot of people know that, so we want to make sure that you're not misdiagnosing that. If you ever feel that your relay is sticking, it's very simple. You don't have to cut the wire over here. You can literally just pull the fuse out of here. Or if you don't want to pull the fuse out of here, you can simply just disconnect 24 volts here. Okay, and when you remove the 24 volts, if your relay was stuck closed, the relay would still be stuck closed, right? So you can also see that kind of resets that countdown. I'm going to sit there, I'm going to go ahead and jump it out again. I can simply just say, hey, is my relay stuck closed because it won't shut off? No, it's working just fine. It's just on a countdown. And then I can test it again. And it's as simple as that. We're going to go ahead and take this and wire it to a blower motor. We're going to explain how the normally closed is always energized by wiring it to a light bulb when the relay is in the open position. And we're going to toggle the blower motor on and off several times. We're going to go over the 5-amp fuse. We'll have a float switch wired up where we can easily break red without having to disrupt power here. And then we're going to take it to the smart board, so stay tuned. Okay, now we're over at the blower wheel, blower motor. All right, this is a 240 volt blower motor, run capacitor and 3 speeds. You can see I'm holding up 3 different color wires. I've got red, blue, and black for low, medium, and high speed. I have a power supply over here, similar to what I had over there, where I have 24 volt secondary voltage control, and I have line voltage here, L1 and L2. We have our blower relay, the HK61E. We have a float switch and a light bulb. So we're going to go ahead and wire this up. I am introducing neutral now. How I'm going to get my neutral is I have an extension cord that I'm just going to plug neutral into, and that'll give me a path. And with that, I can run my light because that needs 120 volts on its own. I'm going to go ahead and take the meter and just show you our power. Between L1 and L2, we have 238 volts. Between R and C, we have 27 volts. And I'm going to go ahead and test neutral. I'm actually going to come up here, see if I have a good connection. I'm going to go ahead and just, yep, I have 120 volts each leg. So neutral is a good path. Let's see here. Let me go ahead and fix that connection, and then we'll go ahead and wire up our light bulb first to the normally closed portion of our relay on the board. Okay, so we're going to run that over. Connect this to the normally closed portion. Let me reroute this wire, and I'm using 10 gauge wire here, so we normally would not use 10 gauge wire, but this is all I had available to me, so it's a little harder to mess with, hence the reason why you shouldn't have to mess with it. Go ahead and take that off real quick. I'll tell you what I'm going to do. I'm going to go ahead and just grab a jumper. I think this would be easier, and I'm going to go ahead and wire this top portion to the back side of my light fixture. Okay, so now we have a good neutral. Now we'll test it because we're closed between normally closed terminal and the common. So if we wanted to test that out, I should have a good path. I should read 120 between here and any one leg of power, so between L1 or L2. And I'm getting 120 volts there and 120 volts there. So neutral now is connected through the bulb back to here. Now we'll change that course of direction, that path, the moment we apply a leg of power up there. Give you an example. If I were to take any one leg of power, I can come over here and we're changing that path so the light comes on. All right, so getting right into it, we're gonna go ahead and wire the high voltage up first. We're gonna go ahead and provide that leg of power back over here to common. Obviously the light's coming on because it's normally closed there. And then we have the normally open portion, which is where I would hook up one of my wires, either low speed, medium speed, or high speed. We're gonna go ahead and just hook up high speed. And so I'm gonna go ahead and connect high speed to my relay. I'm gonna go ahead and disconnect our high voltage for safety. There we go. We're going to go ahead and connect that back now. There. Okay, so everything's wired there, and basically to finish our motor, we got to wire our common leg of power. So we're going to go ahead and take the second line voltage, the second leg, and we're going to go ahead and connect it. And we're going to let our medium speed and our low speed just kind of dangle. If this was in your air handler, you would want to take these off or cut them, strip them back, put a wire nut on it. But our high voltage is done. It's that simple. Let's go ahead and wire up our low voltage, and we're going to utilize our safety switch here, where we couldn't have done that at the CANTEX box because I didn't have a safety switch over there in SS. This is a SS2. So these top three, if you look over here on the screen, you'll see a picture of the board. We got common, common, and common. Then the next three terminals are T for transformer, G for the fan call, and R for 24 volts. Now the fuse is sending a power from T over to R, if that makes sense. So I'm going to go ahead and wire this up. We're going to go ahead and take the top three. I'm just going to take our alligator clip and just connect across a couple of these. And we're going to go right to common. And then we're going to take T for transformer. And I'm going to move some of this insulation that I have on my alligator clip to try to protect this one wire, because the last thing we want to do is short anything out. We don't want to do that. There we go. And now that I made that connection, I'm going to connect it down to R, the transformer, and now we have 24 volts on the load. Now what happens if I close power between R and G, since T is an input, R is an output, I'm going to need power to come out of R. Okay, so I have 24 volts sitting here, and with that, I'm going to connect to one end of my float switch here. All right, and so I just made the connection right here. So now that 24 volts is now sitting over here, providing the switch is closed. We're going to come back out of that switch with our other wire, and now, and this is very difficult, and at the CANTEX box we had a hard time connecting these because when we did that, we had a problem with the amount of space that was available. So I'm going to disconnect 24 volts down here for a second, and I'm going to try to make these connections on the board. I'm going to go ahead and connect G first. and I'm going to run this back to my float switch, and then out of my float switch, I'm going to run it over to R. So really it's out of R through the float switch then to G, but I'm just kind of doing it this way just so I don't touch anything. Let me go ahead and disconnect some of this high voltage as well, so I can get my hands in here. I'm going to go ahead and I'm not using the plug that has all the wires on it. I'm having to just connect to the pins themselves, which is not a lot of room. And so I wanted to do this, and I wanted you to see this. This way you have a respect for why it's important to learn in many different perspectives. This is one perspective that, in my opinion, is very confusing, because in this perspective, we're not able to see everything that's going on. I'm going to go ahead and hook our line voltage back up. The light's going to come on here in a second. Okay, and now the only thing we're waiting for is 24 volts, which I'm now going to take our float switch. I'm going to break power. I'm going to come down here and connect red. And just like that, our relay is closed. Now, somewhere in here, I am making the connection, because what was supposed to happen was nothing should have came on and ran. But because all these wires are so close together, I'm actually crossing somewhere. So I'm going to try to get better connections here. As I showed you earlier, we start disconnecting 24 volts, we can interrupt that time delay. So we're going to try this again. Okay, so we have T and G. So we're going to wire into the float switch one side of G. Okay. We're going to wire into the other side of the float switch and connect this back to R, which is obviously going to be hard, so I'm going to disconnect our line voltage again for my safety. And I'm going to try again to try to make this connect without touching anything. Let me get a little bit more of this insulation, and I think we'll have a better, I think we'll be better this go around. I think we're gonna accidentally energize anything. All right, we'll try this again. All right, we're gonna hook up our high voltage back to L1 and L2. Okay. We're gonna go ahead and connect R, and as long as nothing's falsely connected up there, meaning I'm not shorting anything out because I'm cramming a bunch of wires into it, then the relay should stay in the position that it's in now. And I'm still touching. So here's what we're gonna do. We're gonna go ahead and just disconnect from the R into G. Okay, and we're just going to leave the T terminal connected, and our common terminal connected. I'm going to go ahead and connect this back. And at this point, I still have my float switch here, and we'll play with that here in a second. But what I can do is I can sit here and just take my leads like I did at the CANTEX box, and I can just short up the G in the R, and that will give G power. And now at this point, even though G doesn't have power, it's on a countdown. That countdown is 90 seconds. It's very easy to misdiagnose this. As you see here, I have no G-call, but if I was playing with a bunch of wire nuts, what I was trying to show you, maybe I can get my connections right, is I can release G, take G, release G, take G, release G, and I can have a relay that just seems to never open. And that could make me say, hey, my board's bad, when really it's not. I'm just forgetting that there's a 90-second countdown before that relay opens. I always recommend that you use a timer. Every cell phone's got one. Definitely use one there. If you're ever thinking that your relay is stuck, you can simply remove 24 volts, and that should immediately cancel the countdown, because remember, we're applying 24 volts to our circuit board because it is a working load at all times. And that's how we're able to keep the relays energized longer than the call. All right, we're going to try this again. Still making a connection, so I apologize about that. I'm not going to be able to do it the way I wanted to do it. However, we'll go ahead and just talk about if we were to apply power to the bottom terminal here, okay? You're going to energize the G, and if we are sitting here with our meter trying to find out, do we have a G call? Okay, we don't have a G call. The board's still making the blower motor run. All right, and then typically people apply the G call again, and they release the G call, and they'll do this several times. And what will happen is you will apply G so many times and release it so many times that you're not even waiting a minute and a half in between each one of those. So when you're in this situation, what we want to do is we want to sit here and calculate what that time is. So we can come over here, just get out your phone. And right now we're in an off delay. So I'm showing you what it looks like in the middle of an off delay. We know it's a 90-second off delay. However, it's not going to take 90 seconds for this to cycle off, because we've already put so much time into it already on the off cycle before we put our timer up. So, but in this state of confusion, you don't know where you're at with anything. So, it's very easy to jump the gun and say, I've got a bad board. And a lot of times these boards are misdiagnosed. Sometimes maybe your G, your wire for the blower, is simply just getting power. And see, that was only 42 seconds. Now, that's because we jumped in the middle of it all. So we're going to go ahead and just show you. I'm going to go ahead and hit reset. I'm going to energize this. Release power. And it is a true minute and a half. And so every time you put power on G and you release power from G, you want to be patient and thorough and make sure that you are guaranteeing that 90-second minimum is there. I will always say, if it says 90 seconds, go 2 minutes. And you're always looking for consistency, so you can test these several times. Now you might think, oh, I don't have time for that, but in 5 minutes, you will spend more time misdiagnosing, and you will spend less time correctly diagnosing. So 5 minutes, that is enough to energize and de-energize this board 3 times to see if there's consistency. So 5 minutes is not very long at all. You will spend more time misdiagnosing this thing. And see, just in talking about it just a little bit, we're already a minute into it. 30 seconds more, this thing is naturally going to shut off and put power back on the normally closed terminal. Another 10 seconds, or another 20 seconds. I wanted to show you through the float switch by breaking power and putting power there, making this to be my G call, but that didn't work out for us because obviously I'm not using a plug. And there we go, very consistent. So if we were to take some of these wires away, clean this board up a little bit, it'll make it a heck of a lot easier. And now we can sit there and we can see that I'm only supplying 24 volts on the T terminal and common back to my transformer. And so all we have to do literally is just short the test pins between R and G, which would be the same thing as if you took your wire nuts and you took R and G and just touched them together. That's the same thing as me sitting here and touching them together right here. All right, but as we've been talking about this whole time, I can't convey it enough. It is a 90-second countdown. If you want to see, hey, is my board bad? How do I know if I have a bad board? Well, you can just simply come over here and just unplug, 24 volts from the board, and at that point in time, if the relay was stuck in the closed position, it would still be running. So I know this board is good because it shut off, it opened up. I'm gonna go ahead and connect T, okay? I'm gonna go ahead and connect T again. So now T is connected. Okay, and so now our board is a working load. It has 24 volts. I'm gonna go ahead and jump between R and G, which is the same thing as you taking your two wires, green and red, and touching them together, with your wire nuts off to test this board. And I'm going to show you also when your fuse blows how nothing works. Because T is an input, R is an output, but it's through the fuse. So we'll go ahead and bridge that, get it to run. And same thing, if my fuse were to short out and open up, I'm going to lose that timer. And so with that being said, no matter what, there's always power on that top terminal, so be very careful there. Be very careful there, okay? This fuse is a 5-amp fuse, by the way, if it's a carrier make, Comfort Makers, carrier products. It could be a Payne, Bryant, there's a lot of ICP products. Basically, they require 5-amp fuses. That's what the manufacturer wants. Just because other fuses can fit right here, you don't want to put them in there just because if you do that, then there's nothing protecting your low voltage secondary components in the event that there is a short. Most likely, if this blew, it's because there's a short. Fuses don't just go bad. Also, you never want to bypass your fuse. I'm going to go ahead and show you here when I bypass it that all I'm doing is just closing the circuit. And you're not supposed to do this, but I'm going to go ahead and close this circuit here. That's the same thing that my fuse is doing. And the moment I give power to G, the blower runs. But just like here, if I wind up losing 24 volts because that circuit opens, then nothing's going to run. Okay, so you got to make sure you have a good fuse. You want to make sure your fuse is the right size, and if they are blowing, you want to investigate on what's causing that short. We're going to release other videos that go over shorts and tips and tricks of the trade, and it'll probably be like 4 or 5 part video on low voltage. So so we don't have one 5-hour video. Nobody's got time for that. But we'll go ahead and release that here real soon. As we wind down off of the motors, we'll be getting into other subjects. This is a very good board, the HK61E. It ran the gauntlet in our world for a good 20 years, a little over 20 years. And at the end of the day, it actually made the list for blower control boards that were integrating ECM motors into the trade, and this was what was turning those on and off. So it was a very short period of time. We're going to talk about that when we get to the timeline. but they quickly phased it out and integrated everything into the backside of the motor on the module. So stay tuned. We're going to take it to the smart board. All right, we're at the smart board now. We're going to go over the timeline, and we're going to talk about how to wire this up on the next page. The HK61E, you can see where it appears on the timeline in the early 2000s and where it ended, and it only ran about a good decade. This is pretty much the last PSC motor video we're going to put out. Turn it on and off with a relay or blower control board before we just get into the ECM. This is pretty much where everything's at right now. But we want to know, why did we need this blower control board? Why do we need this PCB? This board was there to give you more efficiency. And we're going to talk about that efficiency, and we're going to try to better understand that if that were to not be there, how would that impact someone's electric bill and their comfort? We're going to get right into it. We have L1 and L2 transformer, a low voltage terminal block. We got the thermostat. We put a light up here just to give us a neutral, and if we wanted to wire that up, possibly we'll wire it up on this video. We have the run capacitor, and then we have our blower motor, common run and start. And this is just a PSC motor here. And then if we look at our board, the image of our board, this is a pretty clear image here. You can pretty much see all the pins, R, G, go ahead and dot these, R, G, T, C, C, and C. And these C's are all commons. Now, you have an integrated fuse, which is a 5-amp fuse, and then we have the JW1 jumper, which is right here. That jumper, if you were to cut that jumper, just put a break in it, then you'll get rid of that off delay that we showed you at the CANTEX box, and that off delay that we showed you on the motor. So we're going to go ahead and wire this up, and we're going to talk about safety tips when we wire this up. For example, when we wire up anything, you're not going to have it as easy as, a mapped out diagram like this. You're probably not even going to have a diagram. So wires that are there were put there, maybe not by the factory, maybe somebody else worked in that unit prior to you, and they may have left some things a little bit strange, right? Not to mention it's a dark environment. Typically it's not within a perfect line of sight, right? It's in a cramped environment. So when you start getting tools in there, it's even a smaller workspace. You may have your shop calling you, asking you when you're done with your call. Hey, hurry up, call us back so we can get you to your next appointment. They're already on the phone, wondering where you're at. Meanwhile, your homeowner's asking you the same question. Hey, are you done? I've got to go. I've got to pick up the kids, whatever the case may be. Long story short, you're taking that pressure, and it definitely puts a strain on one's ability to clearly think through a problem. And one of the things that you need to understand and not forget is when you're dealing with these blower control boards, they literally are there to give you an off delay. So that off delay is 90 seconds on this one. And so 90 seconds is very easy to misdiagnose something. That's a long time. And so earlier at the blower wheel or blower motor, I said, hey, listen, 5 minutes gives you enough time to put power on G, release power on G 3 times within 5 minutes. And if you were holding up your phone and you put your stopwatch there, that's 1.5 minutes plus 1.5 minutes plus 1.5 minutes, and you're not even going to get to 5 minutes. So under 5 minutes, you have enough time to diagnose this thing 3 times the right way. So if you're there for 30 minutes and you still haven't figured it out, most likely it's because you're not being patient, and in conjunction with that, you're supplying power from G, right? And then you're releasing power from G. There's 90 seconds. You're supplying power to G, 5 seconds later. You're releasing power from G. Now it's 90 seconds, this thing's still gonna run. And then you maybe wait 30 seconds and then you put power back on G. And then what you do is you release power from G, so it's now missing, right? That's exactly what your board sees. And at the end of it, you've been there for 15, 20 minutes and you don't know why your motor won't shut off. It could be anything else but the board. But that doesn't mean that the board isn't the problem either. So we want to cover those topics as we wire this up. The first thing we need to do is, how do we wire this up? Let's cover that. Let's first go ahead and wire up everything here. We're going to go ahead and cover the L2 and the L1. All right, so we're going to first cover L2. We're going to take L2 because the transformer happens to be the closest high voltage component to L2. We're going to go ahead and land power there like I show you in all my other videos. Start with one leg of power, and when we're done with that leg of power, then go to the next leg of power. Don't go from one component to the next. For example, I'm not going to wire up my transformer and then come down here and wire up my board, because if I did that, I could accidentally miswire something. As you can see there, that's obviously miswired. So what you want to do is you want to sit there and not wire one component and then go to the next component. You want to wire one leg of power until that leg is 100% done. Now you've had time to verify that one leg, let's just say, for example, if I wasn't careful, I could easily take this and maybe come up here to my top side. Well, now I got high voltage on the bottom side and high voltage on the top side, all because you couldn't read or understand that, between here and here, and between here and here, you're on two different sides of the transformer, high side and low side. So you want to take your time, you want to be careful, and just don't jump into that other leg, or don't try to finish wiring that whole component up. Just wire one leg on that component, and the reason why is just the safest thing you can do. So I have L2 on my transformer. Where else does L2 need to be? That needs to be your question when you're standing in front of this. Well, L2 has to make it to the blower. But before we get to the blower, we have to break that across the relay. So we're going to go ahead and find our common terminal, which would be here, right? There's common. And we're going to go ahead and wire L2 to common. So I'm going to put an arrow here because this is an input. Now, we have two other terminals that are going to supply voltage. We have a normally closed terminal, and we have a normally open terminal. Well, obviously, if we have power here, there's always power here. And if what we're trying to do is get our motor to come on when the board is told for the motor to come on, then we have to go where there's no power until that happens. So that would be the normally open terminal. So I'm going to come out of here as an output, and that's going to wire over here to common on my motor. Now, I can step back, I can verify, and I can just simply, as what we're going to do, we're just going to go ahead and label everything. And where else does L2 need to be? Nowhere else. So now we're done with that leg. So now I can work on the second leg of power. So I'm going to come over and I'm going to wire up L1. We're going to start labeling things. I know that my run winding, it has to be off that same leg of power, right? Now, if you notice I have run and start, they are color-coded red. That's because they're going to be on the same leg of power as L1 here. That doesn't mean that they always has to be L1, because there's nothing special about L1 other than the fact that it's just L1. It's just one leg. It's leg 1. L2 is leg 2. But run and start have to be on the same leg. So I have to pick one. All right. So we're going to go ahead and wire start winding off the same leg, but we have to go in series with a run capacitor. When we do that, this run capacitor, okay, will sit there and release power and provide what we call a third leg. even though it's single phase. All right, and with that being said, I'm pretty much done with L1. I'm going to go ahead and label everything else, but there's nowhere else to land high voltage. We're done. Now, at this present time, path of electricity has L1 coming over here to common, because if you follow the windings, that's what's going on. And because this relay is in the open position, I'm actually not sitting here with power from L2, all right, even though it's wired that way. What we have is we have L1 present here, and as a result of that, if we follow that path back, L1 is present here. So at this present time, I would actually read L2 plus L1 across my relay. And because of that, L2 I know is 120, and it's a different leg than L1, right? And that's 120, so 120 plus 120 is 240. So I would read 240 volts across that open relay. Okay, if I went to my motor, I would read 0 voltage across the motor. Even though if I touched it, I would get electrocuted. The reason why I won't read any voltage, because L1 is the only thing present here, so there's nothing to read against. Now, if I were to maybe put one lead here and then touch the cabinet, if the cabinet's well listed, it's grounded out, bonded to ground, back to your panel and to the earth, then I will read that leg of power. If I'm not well bonded, I won't read anything. If you take your lead and you go from L1 and you ever touch your cabinet and you don't read 120 volts and you read a lower voltage like 12 volts, 18 volts, 30 volts, anything like that, then you have a very bad ground, and that is extremely dangerous. Okay, so what you need to do in that situation is you need to check your ground wire and then follow it all the way back to your disconnect and that all the way back to your panel and make sure it's connected very well. And as long as everything's bonded back to it, then you're gonna have, you'll be fine. So if not, then you can hurt yourself. That's why it's important to use a licensed contractor, because 9 times out of 10, they also hired somebody that has a basic fundamental understanding of electricity. You know, somebody coming out of a school, or maybe they've been apprenticed and been around it long enough to know what voltages they should read. If you're new to the industry, or if you're DIY and you're learning this, then this is a great video for you anyways. All right, so we're gonna leave it like this until these values change. Just like at the motor, we had neutral until we applied 120, then the light came on. So we're not gonna wire anything here to this light, by the way. Maybe towards the end of the video, we'll look at it. So first, we can check off L2. Second, we can check off L1. Now we can go ahead and start wiring our low voltage. All right, so let's go ahead and come out with 24 volts traditionally, and then out of that to the thermostat, right? Wrong. Because remember, we have a fuse integrated on the board, so we're not going to do it that way. How we're going to do this is we're going to have to come out of the transformer and come down to the board, to the T terminal. See these C's? Well, they're going to also have to be available for my low voltage terminal block, and they're going to have to be available for maybe a heater relay, available for the transformer itself. So we're going to have to go ahead and take, like for example, common, and we're going to draw our arrow back to the transformer because that's a path back. Meanwhile, we're going to take our transformer and we're going to send power down here to the T terminal. All right. And so once we do this, then now the fuse is energized on one side, and as long as the fuse is closed, power will make over to here, and then from here back over to R. All right. So it really goes from here to here, here, across the fuse, and then back. All right, so if that fuse ever blows, you lose power here. But now that we have 24 volts here, you know, we're actually going to, I'm gonna go ahead and erase some of these last steps here. okay? Rewind that again and watch that again if you need to. But now we have, as long as our fuse is closed here, like I said, power to T, input over to the 5 amp fuse, one side of it. As long as the fuse is closed, power is now over here, back inside the board, back over to here, power now is out. All right, so let's go ahead and do that again. All right, fuse is closed. So R is a output, and this is going to come up and wire to the board. Now I don't have a float switch here, but typically you would wire this part to a float switch, out of the float switch, and then up here to the terminal block. At this point, your thermostat wire is already running over to here, back to your thermostat. So R is a input to the thermostat, and then common is a path back from the thermostat so we can have a display, right? And we're going to take this common and we're going to run it. I'm going to do that again. Come on this side. We're going to run it, and we're just going to draw an arrow back to the board so we understand our path. So 24 volts, thermostat, common, back to the board, common out of the board, back up to the transformer. There's our path. It gets very busy. It's even harder if I had to show you this inside of an air handler. It's hard to show you at the blower motor. So we took all the terminals and we wired them up. There's only one terminal left, and that's the G terminal. We have O, Y, and G. That Y and O has nothing to do with this control board. But we're going to go ahead and simplify your concern, and we're going to go ahead and just mark those, because you're probably going, well, what happens there? Well, if it's a heat pump, you get a call for the Y call, and you get a call for the O call when you get a call for cool, right? You're always going to get both of those, 24 volts on both of those with the call for cool. However, none of those are going to help you get the blower to come on. For your blower to come on, you need a G call. So we're going to go ahead and give it a G call. Your thermostat should be already programmed to put power out on the G with the call for cool. So, or heat, or fan by itself. With that, you get the G call. The G is now going to come out. It's going to come over. And it is, I'm going to draw that a little bit better than that. Let me do it backwards. There we go. All right, so G is going to come out, come down, and it's going to energize. And the moment this happens, it's only a split second, and now these values are going to change because the machine's going to be running, because it's going to have L2 present. So we're going to go ahead and erase these arrows. And we're going to write L2 here because L2 is now here. Because through the relay, it's going to make. Now, the moment we release the call for G, I'm going to go ahead and just leave it wired here, and where I'm going to erase it is actually right here. Say the thermostat satisfied. You're going to lose power on O, Y, and G. So now you lose power there. Everything's still wired up, so I'm not going to erase this wire, but we lose it at the T-staff. The moment that happens, we lose it here at the board, and now we have a 90-second off delay. So let's talk about this 90 seconds. How is that efficient? How is it efficient for this relay to stay energized and allow the blower to run longer after we lost the call for the condenser to come on? All right, well, let's look at that. If we ran, okay, if we ran for a period of 10 minutes on, right, 10 minutes off, 10 minutes on, 10 minutes off, 10 minutes on, let's see, 10, 20, 30, 40, 50. That's not even an hour. So now we're going to go ahead and do one more, 10 minutes off. And now we can say this is 1 hour. Now within that 1 hour, we came on 3 times. Now I'm not suggesting it's going to run for 10 minutes and then stay off for 10 minutes. This is just a perfect world to try to get to 60 minutes very easily. So 1 hour, which is 60 minutes, 10 minutes on, 10 minutes off, 10 minutes on, 10 minutes off, 10 minutes on, 10 minutes off. There are 3 off cycles. 1, 2, 3, 1, 2, 3, right? And so with these 3 off cycles, each one is 90 seconds. So that means 1.5 times 3, that equals 4.5. So that's 4 minutes and 30 seconds. That's what that means. It's 4.5 minutes. So we're going to take this to the next level, and let's find out within a 24-hour period, what does that mean in a 24-hour period? In a 24-hour period, for every 1 hour, you have 4.5 minutes of the unit of the blower still running with the condenser motor off and the compressor off. So we're talking 1 hour. That equals 4.5 minutes, right? And we want to know what this is over a 24-hour period, because that'll tell us 1 day equals this number. So I'm going to go ahead and get my calculator out, because I'm not trying to sit here and figure this up wrong. So we'll say 90 seconds times 3, that's 270 seconds. I'm going to multiply that by 24, and I'm going to get see if I get that correctly. So I'm going to get 90 seconds for every time it's trying to shut off. We're going to multiply that by 3 times an hour. That's 270 seconds. We're going to multiply that by 24 hours. That's 6,480 seconds. We're going to go ahead and divide that by 60 minutes in an hour. And we're going to come up with 1 day, it runs 108 minutes. The blower runs for 108 minutes in this scenario. 108 minutes. 108 minutes. We'll divide that by 60, and we come up to 1.8 hours. Okay? Put an or there. All right, so let's see what that is in a month. So we're going to say 108 times 30. That's 3,240 minutes. Divide that by 60 minutes per hour, and that comes up to 54 hours. 54 hours. That's more than 2 days. It's more than 2 days. So we can simply say, okay, so 54 hours. We're going to multiply that by 12. We come up to 648 hours. 648 hours. Wow. And we know there's 24 hours in a day, so we're going to divide that by 24. And we come up to 27 days. 27 days. All right, there's 30 days in a month for most months, right? Of course, there's 28 in February, and we know there's some months like March where there's 31. But you're talking about 27 days. That's almost an entire month. That's 1/12 of an entire year that your coil was cold for cooling. And 15 amps of electricity is off at your unit, and you're getting that cold air inside your house at the cost of maybe 1.5 to 2 amps of electricity just on your blower. So when they say it's not advised to cut that jumper, that J1W, that J1 jumper, and it's advised to put this there, they're calculating their sear and they're calculating their efficiencies on many different levels, many different variations on how they get to these numbers. It's not just an expansion valve. It's not just the size of the coil, the size of the cabinet, and how airflow moves through it, and static pressures and compressors that run, that are properly charged, and it's every little thing you can possibly think of. But that one blower control that gave you that in one day, 54 hours out of a 24-hour day. I'm sorry, yeah, out of a 24-hour day, 1.8 hours, excuse me, or 27 days a year of, I wouldn't say free air conditioning, because it's not free to run 2 amps of power, but when you look at the kilowatt hours and the power consumption that you're paying for at the meter with that versus something that is literally 8 times more than that when your compressor is running, right? Outside to do that same thing. Now, you're not transferring the heat from one location to another, meaning from the air handler to the condenser. You're not transferring that heat, but you are gathering that heat and it's staying on the evaporator coil and it's not being redistributed to the house. So that heat is staying there. So you are taking the heat out of there. It is an absence of heat and out of the air. And so that's a really important thing. So these are very efficient. So if you had one go bad, I showed you in other videos how you can just put a relay in there. That's about getting the comfort out of the customer, so they know that, hey, you can get them back up and running. Maybe they don't want to put a big investment into the equipment. Maybe that's all you had, and it's cheaper just to take advantage of being there and utilizing other components that are on your truck stop. However, if you look at, not on a sense of reliability, but in a sense of just efficiency, how much money are you saving with 27 days of getting heating or cooling out of a warm coil or a cold coil just by a byproduct of the blower waiting to turn off for 90 seconds? And that's where that efficiency comes from. So that's very important. That's really cool. And you gotta think like this so you can understand what the manufacturer's intentions were. Why did they give you that component? Now, if I took this out and put a contactor here and I got the motor to come on, as far as the equipment's ability to run correctly, a contactor will make it run correctly. So if this board failed and I ran this with a relay that was just on or off, it is wired correctly. Nothing is bypassed. Nothing is done wrong with that. However, you are taking the ability for this customer to have more efficiency by cooling or heating the home, utilizing less electricity for 1/12 of a year. Okay, so it's not wired wrong. It's just now you can't compare the two and say it's the same. What else? What else do we need to cover on this? I think that's probably the biggest piece, is tying this to the relay and understanding the manufacturer's intentions. That, and the second thing I would take out of this is, that time delay is enough time to misdiagnose this relay. Every time you're putting 24 volts on it, you're releasing 24 volts because you're testing things. That is enough time to misdiagnose this board, because now it won't shut off. How could it? Every time you put 24 volts on it, it's 90 seconds. So rewind the video, get back to the CANTEX box where I was able to have a cleaner image where I can jump that out and show you. Because those are the things that I can't really do here. Here I just have a cleaner way of showing you how to wire it up. So I hope this video helps you out. We're going to get into ECMs. Past that, we're going to talk about all types of other subjects within our trade. We're happy to be able to use YouTube as a platform to educate and share our knowledge with others. We absolutely recommend that you do the same. We have a share button that you can share with anybody on your team. You know, Ideal Conditions, we serve our community with integrity. All of our technicians here worked hard to get to where they're at. Trust when they tell you what the problem is. We also offer second opinions. This is a challenging industry, and we believe most mean well. Those that need knowledge, it's your job to always try to one-up today by learning more than you knew yesterday. I always think like that, and you'll get ahead in your career. You know, never have a day where it's idle, where you didn't learn something new. If there's something that you're told, ascertain what it is, you know, so you can better understand, you know, all types of reasons why you're doing what you're doing. Whether it's you know, somebody that's telling you here's a shortcut, you know, ask them why. You know, we have a lot of bad trade practices within our industry, and we try to clean up and talk about those things on this channel as well. Like our videos that help support the algorithm. Please subscribe, share this with others, leave a comment, and we appreciate all your support. Thanks, and stay tuned.